All right, and now screen share. Takes me a minute to get this set up sometimes. Plugin is required. In this case, install the plugin. All right, let's see if that works. Okay, good. Yeah, I wanted to review a little bit of material. To remind you again, I don't use any new class time for review. I just use a few minutes before the regular class time starts. So if you come in at the regular hour, which is 6:40, 10 minutes past the official start time, you won't miss any new material. But I think sometimes, especially when I'm in the middle of derivations and stuff, it helps to do a little review. So here's backing up a few minutes from where we finished in last hour. This is I don't know how well you can see this, but this is an energy level diagram that shows the results of the ionization potentials in ordinary helium. Here's the ground state of helium down here. If you rip one electron off and carry it out to infinity, you end up with a helium plus ion and then an electron that's sitting at rest at a large distance. And it takes 0.901 atomic units to do that. If you then take the remaining electron and you rip that off and carry it out to infinity, you get a helium double ion and 2 electrons, all 3 particles separated by infinite separation. And that takes an extra 2 atomic units. So if we regard this final state in which all 3 particles are separated at infinite separation as the state of zero energy, which is what we'll do, regard that as 0, then the ground state energy is at minus 2.904. However, the continuum is not at E equals 0, the way that it was with hydrogen. Rather, it's at the energy of minus 2. That is to say, it's at the ionization energy of the very first electron. And the reason is once that first electron has been separated out to an infinite distance, you're free to give it any kinetic energy you want in a continuous manner. So there's a continuum of states that starts here and goes on upwards. So this is the continuum threshold is actually at energy minus 2. What that means is that the bound states of helium lie between an energy of minus 2, with this convention for energy, they lie between an energy of minus 2.904 and minus 2. They lie in this range here. So what I've got is I've got a plot then that I produced last time by hand, and that shows what these energy levels look like. Here's the plot. Here in this energy scale, if you can see this very well, the energy is minus 2 at the top. That's the continuum threshold. And here's the ground state, minus 2.904. These energy levels have been organized by their good quantum numbers. On the left, we've got the para-states, spatially symmetric, and on the right, the ortho-states, spatially antisymmetric. The para-states are associated with spin singlet, which are spin antisymmetric, and the ortho-states are associated with spin triplet states, which are spin symmetric in order to satisfy Pauli. And each one of these two sides, the orbital angular momentum quantum numbers, SP, DF, and so on, they go all the way out to infinity. I've just listed the first 3, but there's an infinite number of them on both sides of this. And the result is that each column of this, there's 6 columns represented here, but there's really an infinite number of them. Each column here represents a definite quantum number, a good quantum number of the system. So it represents a certain symmetry class. So for example, this leftmost column is one in which the spin is 0 and the orbital angular momentum is also 0. That's what this is. These are the singlet S states. Whereas this one over here involves a triplet P. That means the spin is 1 and the orbital angular momentum is 1 also. All right. So this is in effect is the experimental spectrum of helium. And we noticed 3 qualitative features of this spectrum. One is that there is no singlet, there is no one triplet S state. That's a state in red over here that would exist. It doesn't actually exist. But if it did, it would be over here somewhere that corresponds to the one singlet S state over here on this side. Here's the ground state minus 2.904. The second item to notice is what I call the staircase effect, which is if you're on one of these sides, that's to say a given spin value, then the energy is an increasing function of angular momentum. That's why I call it, because it looks like a staircase going up in this picture here. And then the third item, which is maybe the most important physically, is that if the angular momentum is fixed, and also the principal quantum number, I should say N and L are both fixed, then the dependence on the energy is that it decreases as the spin increases. Well, the spin goes from 0 to 1 means it increases, but the energy levels on the ortho side are lower than they are on the para side. That's true for all of them, not just the lowest ones. But anyway, that's the third thing. So part of the goal for tonight is to explain these qualitative features of the helium spectrum on the basis of theory, that's to say good perturbation theory. Okay, so in doing that review, I ran a couple of minutes into our good time tonight. I hope you consider that valuable. So what I'd like to do then is to begin with a perturbation analysis of the helium atom in order to try to understand these qualitative features that we see here. So to do that, let's talk about the Hamiltonian for helium. I'm going to write the Hamiltonian as H0 plus H1. And H0 I'm going to write this way as P1 squared over 2 Z over R1 plus P2 squared over 2 minus Z over R2. And then the perturbation H1 I'm going to write as 1 over R12. Let me give you a drawing here of what the physics looks like. Let's have coordinates X, Y, and Z. Let's have the nucleus, which has got charge plus ZE at the origin, like this. Let's have one electron out here at location, let's call it X1. Let's have another electron at a different location, let's call it X2. And let's call the distance between these two R12. And we'll call R1 the magnitude of X1, so that's the distance from electron 1. Here's an E minus here, and here's an E minus over there. And R2 is magnitude of X2, so that's the distance of electron 2 from the origin. So to go back to the Hamiltonian, you can see that I've divided this H0 up in such a way that it's a sum. It's actually the sum of two hydrogen-like Hamiltonians using the nuclear charge Z, which is right here. It's a Hamiltonian you'd get if you could switch off the inter-electron interaction and have two independent electrons orbiting the same nucleus with no interaction between them. And the H1 is the inner electron potential energy, which of course involves the repulsion of these two electrons. So this is the perturbation setup, and some comments about it before we get started on it. Obviously in perturbation theory, you want the unperturbed system to be solvable, and this one is because it's two independent hydrogen-like Hamiltonians added together. However, you'd also like the perturbation to be small. Now the electrostatic interaction between the two electrons has got a basic charge of 1. You know, they're both a charge of -1. So that's why we get the 1 over R12, whereas the interaction with the nucleus has got a factor of Z. If we're talking about helium, what that means is that these potentials that occur in these hydrogen-like Hamiltonians are roughly twice as big as the perturbation. Well, if you're going to do perturbation theory, you'd like the perturbation to be small, and a half is not all that small. It's not super favorable, let's put it that way. You'd prefer it if it were a smaller number. So this isn't exactly an ideal situation for perturbation theory, but we're going to do it anyway because it's a calculation we can do, and there's not a lot of choices about how to set this up. One remark to make is that if the nuclear charge Z increases so that we're talking about heavier atoms like, like helium, like beryllium or boron, or even helium like uranium, where Z gets to be really big, then this becomes more favorable because this term remains with just a single charge and becomes less and less significant compared to the Z over R1. So this perturbation expansion will work better for higher Z. By the way, we can also go to lower Z. We can take Z goes to 1, in which case helium is converted into H minus, the H minus ion, which I talked about before. And in that case, this perturbation is actually the same order of magnitude. It's like the perturbation parameter epsilon is equal to 1 here. It doesn't look like it's very good at all. Anyway, as I say, we're going to do this perturbation expansion anyway because there's not a lot of choices. And this is kind of the setup that we use for this. All right. Now, this is the perturbation setup. Now, the usual thing that we do in perturbation theory, the first thing we do is you need to understand the unperturbed system. So before we do the perturbation, so let's talk about the unperturbed system here, the H naught. This, as I say, is the sum of two hydrogen-like Hamiltonians with the same nuclear charge. So the Schrodinger equation is separable, and the energy eigenfunctions and are products of single electron wave functions, which are their central force wave functions. So they're specified by central force quantum numbers. Let's call one of them NLM like this for one of these two central force wave functions. Let's put a 1 index on this to indicate that's for particle 1. And let me put 1 subscripts in the quantum numbers for the same reason. We multiply this by a similar wave function with quantum numbers N2, L2, and M2 for the second electron and put a 2 on that to indicate that it is the second electron. And this then is in Ket language, this then is a wave function really in a 6-dimensional configuration space, which is an eigenstate of H0. As far as the eigenvalues are concerned, let me write this way. All right, E0, the 0 means in 0th order perturbation theory. The hydrogen-like wave, by the way, these wave functions, these single particle wave functions are called orbitals. The word orbital here is used in the sense of a single particle wave function. That will be the general meaning of it. It may or may not involve spin. Here it does not. It's just an orbital wave function. But in any case, we say that this is the product of two hydrogen-like orbitals to create the multi-particle wave function. Orbitals are single particle wave functions, which we usually multiply together to create multi-particle wave functions. That's just what we're doing here. In any case, the energies of each separate orbital is determined as in hydrogen only by the principal quantum number and is independent of L and M. So the unperturbed energy depends only on the two principal quantum numbers N1 and N2. And in fact, it's minus z squared over 2 multiplied times 1 over N1 squared plus 1 over N2 squared. This is nothing but the sum of the two hydrogen-like energies for these two hydrogen-like Hamiltonians in these two orbitals. That's all it is. All right. So this is the beginning for the unperturbed wave functions and the unperturbed energies. Now, before we go on, we need to have unperturbed wave functions that are not only eigenstates of the unperturbed Hamiltonian, but also the symmetry operators. In particular, the exchange operator is important. What we'd like to have is, oh, and by the way, let's abbreviate this product. Let's write it this way as N1, L1, M1, N2, L2, M2, giving us a total of 6 quantum numbers to specify this product state as kind of a slightly abbreviated notation. Now we also want the unperturbed eigenstates to be eigenstates not only of the unperturbed Hamiltonian, but also the symmetry operators, of which the exchange of particles 1 and 2 is an important one. And what that means is we want wave functions which are either symmetric or antisymmetric under the exchange of the coordinates. Let's see here. But by the way, let me put this on hold just a minute. This whole perturbation theory on hold, and just remind you of some things that we did in the last lecture. One of the things we determined is that if you want to satisfy for this model of helium, the electrostatic model of helium, if you want to satisfy both find an energy eigenfunction and also satisfy the requirements of the symmetrization postulate, then the way to do it is to first look for an eigenfunction of the Hamiltonian regarded as a purely spatial problem. So if I write it in wave function language, we look for H acting on psi of x1 and x2 is equal to an energy psi acting on as a function of x1 and x2, like that. And you'd also like it to be either symmetric or antisymmetric under spatial exchange. So psi of x1 and x2 is plus or minus psi of x2, x1. That's a way of saying that it should be an eigenfunction not only of the Hamiltonian, but also of the exchange operator E12. Anyway, once we found that, this plus or minus sign here is what I call lowercase E12 orbital. It's the exchange symmetry under orbital exchange. And if I write this wave function in Ket language as just lowercase psi, like that, then the way to construct the state that obeys the symmetrization postulate, which I'll call a capital psi, is to take this lowercase psi, which is just purely spatial, as I've indicated, and multiply by the spin state SMS like this, where S is equal to 0 for singlet if the psi is symmetric, because that makes the spin part antisymmetric, and then vice versa for antisymmetric psi, which is the ortho states, we require the spin to be triplet. So that was something we worked out in last hour. And so to go back to what we're doing here with this perturbation problem, we want to find purely spatial wave functions. That's what this is Ket language here, but it's just for purely spatial wave functions because these are all spatial quantum numbers, central force quantum numbers. Once we solve the spatial problem, we'll multiply by SMS to get the right wave function, including the spin. So that's the project up here above this line. So we do need wave functions, spatial wave functions now, which are eigenstates of E1, 2, that's to say even or odd under exchange. Okay. So one of the ways of doing that is to create eigenfunctions that are even or odd under exchange. Well, let's see. Let's talk about a couple of cases here. Let's talk about case one. What I'll call case one. I'll distinguish two cases here. This is a little simplistic, but it works for what we want to do. Let's talk about case one is the one in which the principal quantum, the central force quantum numbers N1, L1, and M1 are actually equal to N2, L2, and M2. The two are equal to one another. And so let's just call these N, L, and M without subscripts. And if we do, then this product state up above is just the same thing as NLM, NLM, like this. And what you can see is that this is already symmetric under exchange. This is automatically a para state, which means it's symmetric under exchange. And that implies it has to be spin singlet S equals 0. There is no ortho state, which would be a triplet state in case one, if these quantum numbers are the same. What I'll call case two, maybe I've got room for it here. In case two, the quantum numbers N1, L1, M1 are not equal to N2, L2, M2. And in that case, we can get both symmetric and antisymmetric versions. And we write it this way as N1, L1, M1, N2, L2, M2. That's this product state we introduced up above. It's off the page. It's still up here. It's off right here. And then we plus and minus what we get by exchanging it N2, L2, M2, N1, L1, M1, like that. And then to normalize it, we divide by the square root of 2. So if we do this, then this plus or minus sign, which appears here, is the E1, 2 orbital. It's the orbital exchange symmetry, even or odd, indicating para or ortho. These two states with the quantum numbers exchanged have the same energy under the unperturbed Hamiltonian. The energy is just given by the n quantum numbers. It just depends on the sums of the two. So it's the same if you swap N1 and N2. So these two states with the plus and the minus sign have the same energy, but they've got opposite orbital exchange. So they're going to get multiplied by opposite spin wave functions to create the total wave function. All right, so this is some of the setup then of the perturbation theory that we want to do on the system using this H1 as a perturbing Hamiltonian. Before we do the perturbation, still continuing with the analysis of the unperturbed eigenstates, let's now turn our attention. We've taken care of the wave functions now, the unperturbed wave functions. Let's turn our attention to the energy eigenvalues. Well, the formula for them is up above. I just gave it right here. Here's what it is. Just the sum of two hydrogen-like energies. But let's analyze this in a couple of cases. Let's start with what I'll call singly ionized states. Singly ionized states. Actually, it includes the ground state. The ground state plus singly ionized states. These are one in which the first quantum number N1 is equal to 1. If N1 is equal to 1, then the only state you have is 1, 0, 0. Those are the only values for the other quantum numbers. But we'll let N2 be greater than or equal to 1. The ground state then looks like this. it's a 100, and you can see that this is case one. This is to say it's all automatically symmetric, so this is a para state and is necessarily a singlet, s equals 0. This is the case where n2 is equal to 1. But if n2 is greater than 1, then we have 1 over root 2 of 100, right this way, 100 NLM plus or minus NLM 100, where the n here is the same as the n2. N is greater than equal to 2 here. All right. And this is a case 2. All right. So let's plot these energy levels and see what they look like. So if N1 is equal to 1, and let's take Z equals 2, because let's talk about helium for the sake of helium here for that particular case. Then the energy levels, which is, I'll call it 0th level energy levels, depends on quantum numbers N1 and N2, is equal to, here's the formula, there's minus Z squared over 2. If Z is equal to 2, that's equal to minus 2, 4 over 2. So we get minus 2 multiplied times 1 plus 1 over N2 squared. That's the energy levels. And this is equal to, if N2 is equal to 1, which is the ground state, then it's 1 plus 1 times minus 2. I get a minus 4 when N2 is equal to 1. And if we let N2 go to infinity, then that goes to 0 and we get minus 2 as N2 goes to infinity. So in these singly ionized states in which the N1 is equal to 0, the first electron is in the ground state, but the second electron is in the excited state. The maximum energy goes up to minus 2, which you'll notice is the continuum threshold. Something else to notice is that when N2 is equal to 1, you've got the ground state. And in that case, it's purely para, that's a spin singlet. There is no spin triplet part. But when N2 becomes greater than 1, for the excited states, N2 is greater than or equal to 2, then you have both singlet and triplet states because you got plus and minus sign here. The energies, however, are independent of the sign. So that leads us to an energy level diagram for the unperturbed system, which I want to present to you now. And I've got it as a blown up version of a diagram from the notes. So let me present it. It's neater than what I can draw by hand. To get this out of the way here. So it looks like this. These are the unperturbed energies now. And the energies that I just explained, let me see if I can go back to them here, find them again. The energies that I just explained, where did I explain them here? Well, where did I explain them? I've lost it now. Oh, I see, it was on this piece of paper, that's why I've lost it. They range from minus 4 when N2 is 1 up to minus 2 and N2 goes to infinity. So if I list the two principal quantum numbers as N1, N2, here's the sequence of states, which are the singly excited states. Here's minus 4 for the 1, 1 state. That's the ground state of the unperturbed system. And then as N2 increases out to infinity, you get an infinite number of levels that accumulate up at 1 infinity, which is at the continuum threshold you can see here. This is on the para side of the two. I don't know if you can read that, but that says para. On the ortho side, the picture is exactly the same, except there's no 1, 1 state, because that was case 1 where there's no antisymmetric, spatially antisymmetric version of the wave function. On the other hand, the 1, 2, 1, 3, and so on states are the same, have the same energies on both sides. Wave functions are different, but the energies are the same. The energies are the same because in the unperturbed system, the energies only depend on the principal quantum numbers. All right. So these then are the singly ionized states here, as well as the ground state listed below below the energy of minus 2. Now then, they're also appearing in this diagram what we call doubly excited states. I don't know how well you can read them, but here's a 2-2 state. Let me say something about them. Doubly excited states are ones in which both quantum numbers are excited away from the ground state. So let me go back to this page here. if I had a doubly excited state, let's say that N1 is equal to 2, and N2 is greater than or equal to 2. So then I get E0 of N1, N2 is equal to minus 2 times 1 over 2 squared, which is 1/4, plus 1 over N2 squared. And this goes from when N2 is equal to 2, so it's 1/4 plus 1/4 is a half, it goes from minus 1 when N2 is equal to 2. And as N2 approaches infinity, it goes to minus 1/2 as N2 goes to infinity. And so what you get is a sequence of doubly excited states. And here they are. They are listed like this. Here's the 2, 2, 2, 3, and all the way out to infinity. It ranges between energies -1 and -1/2, as you can see. And over here is a similar set of states on the ortho side. Now these are states of the, as I emphasize, this diagram here refers to the eigenstates of the unperturbed system. We haven't dealt with the perturbation at all yet. But anyway, this is the energy level diagram that we get for those states. Now, the doubly excited states are interesting because they're an example of discrete states embedded in the continuum. For example, this 2,2 state here is a product of two normalizable hydrogen atom orbitals. So it's a normalizable wave function. It's a discrete state. However, it coincides in energy with a continuous set of states in which one of the electrons is in the ground state, the n equals 1, and the second one has been excited into the continuum. And the second state is in the continuum. You can give it any energy you want, so you can give it the energy of the ground state of the one electron that's in the ground state, plus any energy you want. So you can make it range continuously past these discrete states. So from the standpoint of the spectrum, this, as I say, is discrete states embedded in the continuum. Now, I want to say some things about those states before we go back to the perturbation theory. One of the questions is, what the heck does that mean? Does helium really have discrete states that are out there embedded in the continuum? And the answer is no. This is only for the unperturbed system. We haven't turned on the perturbation yet. But the question is, what happens when we do turn on the perturbation? Well, if you just ask about the spectrum and nothing else, the answer is kind of boring, because what happens is that these discrete states that are embedded in the continuum in the unperturbed system, in effect, sort of dissolve into the continuum, so that with the perturbation turned on, there's nothing but continuum states there. There's no evidence anymore. There's no resolution of the identity involving a discrete state anymore. It's just an integral over the continuum. However, that's not to say that the system, from a physical standpoint, doesn't somehow sort of remember that there are discrete states embedded in the continuum out there. And this shows up in a number of different ways. One of them has to do with photoabsorption cross-section. Let me say some things about that. So photoabsorption in the case of helium that I want to talk about here is where we shine a beam of light onto helium, gamma onto helium, photons, helium. And what we want to see is the reaction in which the photon is absorbed, the helium is created into an ion, and an electron is ejected. Let's look at that reaction. Now, the ground state of, if I go back to the real energy diagram of helium, the ground state is at -2.904, and the continuum threshold is at -2. So you need to have a photon energy of at least 0.904 atomic units in order to eject an electron. You've got to have at least that amount. So if we plot as of course, one can determine this experimentally, as a function of energy, we plot the cross section for this reaction. There's not until we reach a 0.904, the ionization potential of the first electron, that the cross section is strictly 0 out to there, because there isn't enough energy. But then what happens is you start to get some cross section for the ejection of an electron. It rises up like that. except after a while, you come to a place where suddenly there's a big enhancement in the cross section like this, and further up, there's other big enhancements. So what's going on here? What's going on here is that these enhancements occur at the nominal energies of these doubly excited states. And roughly speaking, what's happening is that the helium atom absorbs the photon kicks one electron, excuse me, I didn't say that right. It kicks both electrons into excited states, that's i.e. doubly excited states. And those have approximately some kind of a discrete spectrum. They do in the unperturbed system. And so they when the energy is right, they'll end up in one of these doubly excited states. And the fact that the cross section enhances at that point means that those states are particularly stable. So the idea is that this reaction actually proceeds in two stages. The first one is one where H helium goes into a doubly excited state, which I'll call He star. And that lives for a while, and then it decays into helium plus E minus, meaning that one of the two excited electrons drops back into the ground state and the other one gets ejected. So you can picture a mechanism here whereby what was originally two electrons in the ground state, they both get excited into these doubly excited states. After a while, they interact with one another, one then dropping back into the ground state and the other one getting ejected. This electron, which is ejected in this manner, is called an Auger electron. This is called the Auger process. Auger is French, obviously, pronunciation. Doesn't have anything to do with orange juice. And anyway, these are Auger electrons that are created in this manner. Now, this doesn't have to be, this setup doesn't have to take place by photons. You could direct an electron beam against a helium atom, and if the energy is right, you'll get the same phenomenon. You'll knock it into a doubly excited state, and then it undergoes a subsequent decay by the Auger process, ejecting an electron. Okay, so
this,
yes,
this process only happens when it's just the right energy to actually get it to kick up into a state, right? So if you exceed that energy, it just sends an electron straight to infinity.
Well, if you yes, that's correct. Yes, in a sense, that's correct. There's a question of timing here. You see, so for one thing, this is not a precise energy. There's some width here to this. I don't want to go into too many details, but these are not energy eigenstates, strictly speaking. They're resonances, and so they have a certain width. So there's a certain range of energies over which this process takes place. But you're kind of right. If you're out here in the desert where you're not near one of these resonances, then effectively what happens is that one electron just gets kicked directly out to infinity, and that's it. But in the neighborhood of these resonances, you get the excitation of both electrons simultaneously by the same photon. At least that's a classical picture of what's happening.
Is there a chance, even when you're at one of those perfect energies, that one electron just gets kicked straight to infinity?
Yeah, but that's kind of like only a partial contribution to the cross section.
Okay.
Yeah. Most of it's coming from this, in effect, this resonance with this doubly excited state. Okay.
Got it. Thank you.
Yeah. So now this is interesting it's interesting to think about this process classically. The mechanism so you have two electrons in an excited state. The mechanism whereby one gets ejected and one drops into the ground state is they're orbiting around, and then they have this is a classical picture of it. And then they have a close encounter with each other, and one of them loses energy and falls back into the ground state, and the other one gains energy and gets ejected. Well, things like this go on in the solar system all the time. A comet passes close to Jupiter, Jupiter loses a tiny amount of energy, which means nothing to Jupiter. The comet gains energy and gets ejected from the solar system. In fact, that's one of the things Jupiter does is it sweeps out junk out of the solar system, probably making life possible on Earth, because otherwise we get collisions and life would be extinguished here. So it serves that purpose. Jupiter is so massive that it's energetically favorable for Jupiter to move slightly closer to the sun and eject all the other planets and asteroids and comets and everything out of the solar system. Certainly this happens one at a time with small objects like asteroids and spacecraft, deliberately by spacecraft that are sent by, to get gravity boosts from the planets. Mariner spacecraft did that. It's now leaving the solar system. But energetically, it'd be possible for this to happen to all the planets. So there's a question then in celestial mechanics about, will that ever happen? Is that possibility for the real solar system? In other words, is the solar system stable in the long run? It's evidently stable for long periods of time because, we are here after 4 billion years of life on Earth. We're still here. But will it, if we waited for a much longer time, would the Earth get ejected by Jupiter? And actually, the current theory indicates that it probably would. The solar system is ultimately chaotic, and things are going to get ejected eventually. But be that as it may, this gives you an idea of sort of a quantum version, or this is a classical version of what's happening with these decays of these doubly excited states. So in a sense, these doubly excited states have a lifetime, and in a sense, the lifetime is governed by how long it takes for the two electrons to have a close encounter. If their quantum numbers are relatively far apart, so the wave functions don't overlap very much, then they can last for a long time, kind of like the Earth and Jupiter stay in their respective orbits without tangling up. And so some of these resonances actually have very long lifetimes, and they're almost like bound states, but not exactly. So there's a whole story here about resonances in these doubly excited states. All right, now this is something of a digression because it's an interesting digression, but I mainly want to talk about the perturbation theory for the bound states, which are, as you can see from this diagram, are all singly excited. So let's go back to that and talk about that. So for those, there's actually two cases to talk about. There's the ground state itself, and then there's the excited states here and here. So let's do the ground state first, and we'll worry about the others later. So the ground state is particularly easy to analyze because it's non-degenerate in the unperturbed system anyway. And I'm just talking about the spatial part now because that's all we want. But it's non-degenerate because the quantum numbers are 1, 0, 0, 1, 0, 0. And as I keep saying, that's case one. So it's strictly on the para side. As to say, when n is equal to 1, then the L and M quantum numbers are automatically determined so that this is non-degenerate. Therefore, the energy shift in the ground state in first order perturbation theory, which I'll write like this with the parentheses indicating the order of perturbation theory, is just the expectation value of the perturbing Hamiltonian with respect to the unperturbed eigenstate. So it's 1, 0, 0, 1, 0, 0, sandwiched on the perturbation, which is 1 over R12, 1, 0, 0, 1, 0, 0, like so. Now, if we write this as an integral, spatial integral, it's an integral over a 6-dimensional configuration space of the two particles. So I'll write it as d cubed x1, d cubed x2, like this. And what we've got here is on this first bra and ket here refers to particle 1, and the second one refers to particle 2. That was the way I defined things. So we have a psi star over here and a psi there, and this is the 1, 0, 0 wave function of position x1, particle 1. That gets absolute value squared. And for particle 2, we've got a psi 1, 0, 0 of x2, absolute value squared. And then the denominator is the Coulomb denominator, which is the distance between the two particles, absolute value of x1 minus x2. So that's the energy shift according to first order non-degenerate perturbation theory. The interesting fact about this energy shift is that it has an electrostatic interpretation. We're using atomic units here, so the charge in the electron is -1. That means the charge density for electron 1 as well as for electron 2 is equal to minus the absolute value of the wave. The square of the wave function is the probability density. If we multiply it by the charge of the electron, which is -1, we can interpret that as a charge density. It's an interpretation of the probability density. And so what you see here is that this has the form, it's a form that I hope is familiar to you from electrostatics. It's the integral of the product of the two charge densities over a 6-dimensional space divided by the Coulomb denominator. This is what you'd call the mutual energy, electrostatic energy of the two electron clouds. What it represents physically is what you'd get if you took these two electron clouds as separate clouds. They're spherically symmetric, you see, because they're ground state. But imagine them separated at an infinite separation, and then you bring them together. Of course, they repel each other. You bring them together until they exactly overlap. And the energy that's required to do that is what this integral is. So if we think about our system of helium here, what we've got in the unperturbed system where the inner electron potential is turned off, is we have two hydrogen-like 1s orbitals for nuclear charge of 2 that are just sitting right on top of each other like that. And this, as I just said, this energy correction is the electrostatic energy involved of those two electron clouds. Now, okay, so let's work on working this out to get an answer for this. This is just doing an integral. It's an integral in 6-dimensional space, but the integral is basically not hard to do. At least the outline of how to do it's not hard to do. Some of the algebras are complicated, and I'm just going to outline how we do an integral like this. So in the first place, the psi 1, 0, 0, the wave function of x vector like this. If you write it in atomic units, it's the nuclear charge z cubed divided by pi to the 1/2 power. That's the normalization, and then e to the minus zr. That's the ground state wave function for nuclear charge z in atomic units. And so here I've got 4 copies of psi 1, 0, 0, so the normalization gets raised to the 4th power. So that gives me a z to the 6 divided by pi squared. And then I have an integral over the two position vectors d cubed x1, d cubed x2 like this. And then the product of the wave functions, each side gets squared. So the the e to the minus zr is going to turn to e to the minus 2zr. I get e to the minus 2z times r1 plus r2. R1 because there are 2 different electrons here. And then this is divided by the Coulomb denominator. Now the Coulomb, and I'll write this out here as 1 over the Coulomb denominator, x1 minus x2. So this is just putting in the wave functions. Now the Coulomb denominator, by standard methods in electrostatics that you can find in Jackson's book, can be expanded in Legendre polynomials. This is sum from L equals 0 to infinity of r less than to the L divided by r greater than to the L plus 1 times the Legendre polynomial PL of cosine gamma. And to explain gamma, I need to make a diagram here. Let's have coordinates x, y, and z. Let's have the 2 electrons here like this. Say here's electron 1, here's electron 2. So this is distance r1, this is distance r2. And the distance between the 2 electrons is r12. And here's our nucleus with charge plus ZE. Well, the angle gamma that I've introduced here is the angle in the direction between the 2 radial vectors like this. So this is the Legendre polynomial expansion of the which is really a Green's function, this Coulomb denominator. And in some sense, this is the definition of Legendre polynomials. This is where they came from originally. Legendre was studying this denominator. He was doing gravitational problems, but it's the same math. Anyway, that's how he invented his polynomials. These Legendre polynomials can be expressed in terms of YLMs by using the addition theorem for spherical harmonics, which we proved last semester. This gives us 4 pi over 2L plus 1 times the sum over magnetic quantum numbers that runs from minus L up to plus L. And then we have a YLM of omega 1 times a YLM complex conjugate of omega 2. Like that, that's what the addition theorem is. These integrals here, of course, can be transformed into spherical coordinates, in which case you're going to have radial and angular integrals. So to make a long story short, the angular integrals are pretty easy to do. If I'm, for example, integrating over omega 2, I just need to integrate a single YLM. It's easy to integrate one YLM. Here's the integral. You see, it's integral d omega 2 of y LM star of omega 2. How do we do this integral? We do it by noting that y00 is equal to 1 over the square root of 4 pi. It's constant on the sphere. So I can put in a y00 of omega 2 here if I multiply by the square root of 4 pi, and it doesn't change the value of the integral. But now you can use the orthonormality, and you see you get the square root of 4 pi times Kronecker delta L0 to Kronecker delta M0. And this means that already on doing the omega 2 integral of the 6-dimensional integral, the M sum is going to reduce to a single term M equals 0, and likewise the L sum will also reduce to a single term. By the way, I forgot to say that this R less than and R greater than stuff, let me explain what that means. If you've looked at Jackson's book, you know. R less than is the minimum of the distances R1 and R2. and R greater than is the maximum of the two, like so. In any case, by similar techniques, you can do the other angular integral, and what's left over is just purely radial integrals. These are now radial integrals of polynomials times exponentials. They're basically incomplete gamma functions. The integrals are elementary, and for lazy people, you can use Mathematica and get the answer without much trouble. It's not that hard to do it by hand either. I've done it that way. Anyway, to make a long story short, what we get when we do this calculation is we get the delta E of at first order perturbation theory of the ground state. There should be a 1 there. It's a 1. That's first order perturbation theory. Turns out to be equal to 5/8 of the nuclear charge Z. Okay. Now the energy at 0th order of the ground state was minus Z squared over 2 times 1 over N1 squared plus 1 over N2 squared, and that's just equal to minus Z squared. So we can say that the energy in first order perturbation theory of the ground state then is equal to minus Z squared plus 5/8 Z. So that's a nice result. It's a first stab at perturbation theory and understanding the effect of the inner electron potential. Let's look at this energy and see how well it does in various cases. I'll make a table here. I'll start with the nuclear charge Z, and we'll have the atom like so. I'll fill in the table as we go. So let's do 2 atoms. Let's do H minus and let's do helium. Z equals 2 is helium, H equals 1 is H minus. Remember, H minus is really a marginal case for this theory. Let's put in the E0 ground, meaning in the unperturbed system. And let's put in E1 ground, which is what we get when we include the first order perturbation theory. And then since we have experimental results, let's put in the exact ground state energy. Compare these. Let's do it for helium first. So for helium first, the E0 ground was -4. Actually, allow me to put this table that I'm developing on hold and go back to this diagram that I was showing you earlier. This is the diagram of the unperturbed energy levels. And right now, of course, we're working on the ground state here. If we compare this diagram of the unperturbed energy levels with the exact energy levels, which I sketched by hand here earlier, if we compare the two, let's see what the differences are. So one of the differences is that in the unperturbed system, the energy levels are only determined by the principal quantum numbers, and they're not segregated by the angular momentum. The reason being is that they're hydrogen-like orbitals and the energies don't depend on the angular momentum. Whereas in real helium, they do. So we separate them out by L equals the S waves, P wave, SPD, and so on, these columns. So that's one obvious difference. Another obvious difference is that we have the energy levels are the same on both the ortho and para sides, whereas in real helium, the triplet states are lower in energy than the singlet states. That was our item number 3 here that we noticed. Another fact is that in real helium, the energies depend on the orbital angular momentum. That's this staircase effect here, which they don't over here. I just explained why. However, there's an interesting feature. The fact that there, even in the unperturbed system, the fact that there is no 1-1 state over on the ortho side, that's because this is case 1. And in case 1, the spatial part of the wave function has to be symmetric. There is no antisymmetric version of it. This already gives us an explanation for why there's no 1 triplet S in real helium. Because this 1 singlet S obviously grows out of this 1-1 when we turn on the perturbation. And if there were a 1 triplet S over here, it would have to grow out of some 1-1 state over here on this side. But there is no state over there. So we already get, without even doing any perturbation theory, we get an explanation for one of our 3 items here, why there's no 1 triplet S. That tells us why the ground state you see is a para state, not an ortho state. All right, now to go back to the numbers that we just got for our perturbation theory. Well, before I go back to the table of numbers, let's look in this diagram. The actual ground state energy here, well, the actual ground state energy here, let me draw it in with a blue pen, is at minus 2.904. Minus 2.904. So you can see that the unperturbed ground state is pretty badly off. It's down way too far. It's way too low. So let's go back to our numbers now and see what they give us. So -4 was the unperturbed energy. What happens when we add the correction? It's 5/8 Z, so that becomes 5/4, 1 1/4. 1 1/4 added to -4 gives me minus 2.75. And this compares to the actual ground state, which is 2.904. And if we draw this on this diagram here, you can see what the effect of first order perturbation. Here's the result from first order perturbation theory. We've done this. This is the correction. You see, it's covered most of the gap to the correct ground state and actually overshot by a certain amount. Most of it does, but that's only a small fraction. It did pretty well, considering that they, in some sense, the perturbation parameter is just 1/2. It actually did pretty well. All right. Now, what about H minus? Here the ground state energy is -1 because it's just Z squared. If I add 5/8 to it, I get -3/8, which is minus 0.375. And the exact ground state energy is minus 0.528, as we know from experiment. Okay. So this table then summarizes the result of first order perturbation theory on the ground state. Now, there's some questions that we can ask about this as an example of perturbation theory in a real problem. Suppose we didn't have the experimental data here. What would we make of these numbers? So perturbation theory has just given us a number. The ground state is estimated at -2.75. What does that tell us? If we didn't know the real answer, it doesn't, it's a little disappointing if you think about it. It's like using perturbation theory, you know, there's, it looks like we don't, I mean, if we use variational principle, we at least get an upper bound of the ground state energy, but this is not the variational principle. This is just perturbation theory. So the question is, do we even know whether this answer is too high or too low? Much less how far it is high and low. You know, that's the next question. Well, as it turns out, when you're doing perturbation theory on the ground state, it turns out that the estimate from first order perturbation theory, standard first order perturbation theory, is variational. What that means is that there exists a trial wave function that gives the same energy as perturbation theory, first order perturbation theory. And therefore, the result of first order perturbation theory actually is rigorously an upper bound to the ground state. So that's a little better than we had a few sentences ago. This 2.75 is an upper bound. In fact, indeed, we see that it really is. But I'm saying even if we didn't know that, we'd know it was an upper bound. The -4, of course, is a lower bound because the perturbation is a positive operator and can only raise energies. So that would give us a, you know, two bounds on the ground. So the -4 lower bound is not very good. It'd be better if we could improve that. All right. Anyway, that's some of the aspects of analyzing these numbers. Now, in the case of H minus, there's another issue that's actually even more interesting. And that is that the perturbation theory answer, which I just explained is also variational, is minus 0.375. So again, if we didn't have any experimental data, we wouldn't know what the ground state energy was. In fact, we wouldn't even know if there was a ground state. And at a certain point in history, it was not, I mean, it's experimentally known that H minus has one bound state, period, that's all. But there was a point in history where that wasn't known experimentally. So putting yourself in the shoes of a theorist in those days, you have a theoretical problem. Can we predict theoretically whether or not H minus exists as a bound state? Well, if we had been able to get a variational estimate on the ground state energy, which was below the continuum cutoff, below the continuum threshold, then that would prove that there was a bound state because there had been energy below the continuum threshold. But we didn't do that because the continuum threshold is at -0.5 and our estimate is above that. So as theorists here, we have failed to prove that H minus exists as a bound state because our number wasn't low enough. All right, so that's something to keep in mind. All right. Now, so that's the analysis of by first order perturbation theory of the ground state of helium. Let's now move on to the excited states of helium. We'll do all to do the excited states. It's only necessary to do the singly excited states, because the perturbation, as I keep saying, is a positive operator and can only raise the energies. And all of the doubly and other higher excited states are already in the continuum. And so if you raise their energies, they're not going to be bound. So the only possibility of getting bound states comes from singly excited states in helium. So let's look at those. So what that means is we want the N1, L1, N1 to be 1, 0, 0. We want to look at states that look like this, as 1, 0, 0, NLM, where I'll just write NLM for the second set of quantum numbers. And these then get plus and minus NLM 1, 0, 0, like this, in order to symmetrize or anti-symmetrize them to give the right spatial exchange symmetry, and I'll normalize it with 1 over the square root of 2. So these then are the unperturbed eigenstates, singly excited unperturbed eigenstates of the Hamiltonian, which are not only eigenstates of H naught, but also of the spatial exchange operator E12. Now then, the perturbation, of course, is the same as before. It's the inner electron potential. Now, these are eigenstates of the operators I just mentioned, but they're not eigenstates of all of the symmetry operators, at least not obviously, all of the symmetry operators of the Hamiltonian. That includes the operators L squared and L sub z, as well as E12. E12 we took care of. That's given by this quantum number there, that plus or minus. That's the exchange, spatial exchange quantum number. This is E12 orbital. So this is the quantum number E12. I'll use a lowercase for the quantum number and a capital letter for the operator. Now, but we'd also like them to be eigenstates of L squared and LZ, because those are good quantum numbers of the whole Hamiltonian. Well, actually, these states that I've written down are eigenstates of L squared and LZ. By the way, the L squared and LZ refers to the total L, which is L1 plus L2. There's a total orbital angular minimum of both electrons. And so this is the square of that vector and the Z component of that vector. So it turns out that these unperturbed eigenstates actually are eigenstates of capital L squared and L squared and LZ. And the reason is that one of the two electrons is in an S wave, so its angular minimum is 0. So in effect, what we're doing is we're combining together a 0 crossed with L to get the total orbital angular minimum of the two states. And that just gives you L, because 0 doesn't do anything, combining with an S wave. In other words, this is an eigenstate written out. This is an eigenstate of capital L squared with quantum number given by lowercase l. Let's do this notationally. Let me write this, see if I have room to write this here. Let's write this as capital N, capital L, capital M sub L, and plus and minus. And let's define this to be this state here. I hope you can read that. And I'm using capital letters here because I want to use capital letters to indicate the quantum numbers of the entire atom, whereas I use lowercase letters for the quantum numbers of the single electron. In this case, however, they are the same. So big L equals small l, big M sub L, or just call it big M, I don't care. Big M is equal to small m. And as far as n, let's let the big N be the same thing as the small n, just for consistency of notation. And the plus or minus here is the same thing as that plus or minus there. Okay. So these really are eigenstates of all these operators. Now then, we have to go through this because these excited states are degenerate, and we need to think about degenerate perturbation theory. So what we want to do is take this N, L, M plus and minus, sandwich around 1 over R12, N, L, M plus or minus, like this, and then consider the issues of degenerate perturbation theory. The energy eigenvalues are determined by the principal quantum number capital N, which is the same thing as lowercase n. It just tells the quantum number of the second electron that's in the excited state. It doesn't depend on the L and M quantum numbers, nor for that matter on the exchange symmetry, the plus or minus. So the last three quantum numbers, L, M, and plus and minus, identify the energy eigenstates inside a degenerate eigenspace of the unperturbed system. And therefore, by the rules of degenerate perturbation theory, we ought to put primes on those three quantum numbers and consider a matrix in which those quantum numbers are varied, whereas the n's are not. However, as has happened a number of times already last semester, it turns out we don't actually need the primes. And the reason is that this operator actually commutes with total L squared as well as total LZ as well as exchange. Well, it commutes with exchange pretty easily because it's just obvious that 1 over R12 is the same, is invariant in the exchange of the electrons. It commutes with total L because total L is a generator of orbital generator for the coordinates of both electrons, L1 and L2. And 1 over R12 is the, just to write it out, it's 1 over x1 minus x2. And if we rotate both x1 and x2 by the same rotation, obviously the magnitude doesn't change. So it commutes with the operator L vector, all three components of it, and therefore then any function of those components, including L squared and LZ. And the result is the primes are not needed on any of these quantum numbers. So to do this problem right, you need to think through degenerate perturbation theory and convince yourself that the matrix elements are actually diagonal in all these quantum numbers when we set it up this way. But this, of course, then reduces the problem to what is essentially non-degenerate perturbation theory, because we just need to find the diagonal elements, which are the energy shifts. So that means that this quantity here then is an energy shift, let's call it delta E. It's at first order perturbation theory. And this depends on, what does it depend on? NL, depends on NL and the plus and minus. It does not depend on the magnetic quantum numbers. There's only one of them, they're the same on both sides. It doesn't depend on the magnetic quantum number because of the Wigner-Eckhart theorem and because of the operator in the center is rotationally invariant. So it's therefore independent of magnetic quantum numbers. But we can't expect it to depend on the other three quantum numbers, the NL and the plus and minus. In fact, it will turn out to do so. So that's what this is. Let's calculate this. Let's get an idea of what's involved in calculating it anyway.
Professor, can I ask a quick question?
Yes, sure.
So before you were talking about how the singly excited states are the only ones with bound states, so do bound states beyond, or I'm sorry, do states beyond the first singly excited state, do they just not exist, or do they have very small lifetimes?
So the bound states of the unperturbed system, which are above the continuum threshold, are discrete states embedded in the continuum. And if we applied bound state perturbation theory to them, what we'd get is we get nominal bound states. However, their energy would still be in the continuum. In fact, because the perturbation can only raise energies, it's just going to raise them up and they'll still be in the continuum.
Mm-hmm.
However, they aren't really bound states anymore because they're now coupled to the continuum. In bound state perturbation theory, if you'll recall, we had these energy denominators and we worried about what happens if you had other states that were too close by, and we wanted to go to nearly degenerate perturbation theory and incorporate them also into the Hamiltonian, into the set of states that we diagonalized. Perhaps you remember that there was a homework problem on that with the Zeeman effect.
Yeah.
Well, look at what we've got now. We've got a bound state embedded in the continuum. Not only are there states nearby, there's a whole continuum of states, and some of them are as close to our state as you want. They come arbitrarily close.
Mm-hmm.
So bound state perturbation theory, the way we developed it last semester, does not apply. One needs to do some other version of theory in which you take into account the coupling of that discrete state to the continuum of states that are nearby. Now it's going to be most strongly coupled to those that are closest in energy, but there's going to be kind of integrals now instead of sums. That's the idea. So there are ways of doing that, but it's not bound state perturbation theory, which is what I'm talking about now. If you do those those more sophisticated methods of perturbation theory, as I mentioned earlier, what you'll find out is those discrete states actually no longer become discrete. They become now unbound also. That's because they're coupled to these other unbound states, and it gives them wave functions that extend to infinity. Physically, that indicates the probability which leaks out from it's sort of locally trapped, but it steadily leaks out in such a way to produce one electron traveling off to infinity, another one dropping back into the ground state. Think about we had another homework problem last semester in WKB theory where we had the scattering one-dimensional scattering problem where it tunneled through a well and reached a, excuse me, it tunneled through a barrier and reached a well inside. I hope you remember that. And what we found is that when the scattering energy was raised up and down, you could make it come close to one of the Bohr-Sommerfeld levels inside the well. And when you do that, you find that there was a strong dependence in the phase shift of the scattered wave. Also, what happens is there's a great enhancement in the part of the wave function which is inside the well. Roughly speaking, what's happening in that problem is you've got a state inside the well. It looks like a bound state. It's close to or on a Bohr-Sommerfeld quantization condition for something inside that well. It wants to be a bound state, but it's slowly tunneling through the barrier and leaking out. As it does so, it's connected. The wave function actually connects through the barrier to, a wave function that extends out to infinity. So it really isn't bound at all. You see, it just looks like it is. And that's kind of what's going on here too, is that what was a bound state in the unperturbed system is now coupled to wave functions that extend to infinity. And there's a kind of a tunneling that goes more like a tunneling in phase space now rather than configuration space. But in any case, that indicates the tunneling indicates a leakage out or a slow decay out into a new state of the system in which the Auger electron's been ejected and the other one's fallen back into the ground state. Does that answer your question?
Yeah, no, that actually makes sense. Thank you.
Okay, good. That's a good question. There's a lot of interesting aspects to this problem. All right. Now let's see, where was I? The problem is to evaluate this. I think that's the next step. So allow me to do that. So if we just write this out using the NLM here with 1 over the square root of 2, there's going to be a factor of 1/2 here. And we're going to get 2 terms. They're going to look like this. We get 2 direct terms, the 100 NLM like this with the H1 in the middle, 100 NLM. And then another one where the NLM comes first, 100 H1 NLM 100, like so. Let's do that. And then we get the cross terms, which come in with a plus and minus sign. And that's going to be 100 NLM here on the left, H1 in the middle, and then reversed on the other side, NLM 100. And then we get plus NLM 100, H1 and 100 NLM, like so. So just taking these 2 terms for both the bra and the ket gives us a total of 4, and multiplying it out, this is what you get. All right. Now these 2 terms here, the upper 2 terms are equal, and the lower 2 terms are equal too. If you look at it, it's not too hard to see. There's an integral for this expression here, and if you just swap the x1 and x2 variables, which are dummy variables of integration, it'll just swap the two orbitals and make these 2 things the same. And it's similar for the lower two terms like this. So the result is that the energy shift in first order perturbation theory, which ought to depend on these quantum numbers n, l, and the plus and minus. I'll put a 1 here, meaning at first order perturbation theory. This can be written in the following way. I'll write as JNL plus KNL, plus and minus KNL. Or the JNL is either one of these 2 integrals up above. Think about writing this out in wave function language. The first set of quantum numbers is for the particle 1, and the second set of quantum numbers is for particle 2. So you've got a psi star and a psi for particle 1 and with quantum numbers 100, and a psi star and a psi for particle 2 with quantum numbers n, l, and m. So this J and L then is an integral. It looks like this. It's d cubed x1, d cubed x2, and then we have psi 100 of x1, absolute value squared, Then we've got psi NLM of x2, absolute value squared, divided by the Coulomb denominator x1 minus x2. And so that's the J integral here. Now, the K integral is a plus and minus part. So that's this part here. What's happened is the orbital labels are swapped. So we got a psi star 100, psi star NLM, a psi of NLM, and a psi of 100. So this is equal to integral. Just write it out explicitly. D cubed x1, d cubed x2. Am I running off the paper yet? Not quite. So we have a psi from here, 100 star of x1, a psi NLM star of x2. We then from here we have a psi NLM with no star of x1. And from here we have a psi 100 of x2 with no star. And this is also divided by the Coulomb denominator, x1 minus x2. And as I say, the energy shifts are the J plus and minus the Ks. So these are two kinds of integrals which occur in this type of perturbation theory. And if you ever do any condensed matter work or almost any kind of work with electrons, you'll become familiar with these types of things. This is called a direct integral, and this is called an exchange integral. If I can spell exchange in the space I have here. All right. Let's look at the direct integral first, because there's an interpretation for it. Again, this is an electrostatic interpretation. The JNL is has the interpretation of being the electrostatic energy needed to bring together these two charge clouds, one being the ground state and the other being the NLM excited state, regarded as rigid distributions of charge from an infinite separation into their final configuration in which their centers are on the nucleus. That's what the Coulomb, integrating the product of the charge densities divided by the Coulomb denominator, that's what that gives you. In fact, this J is a generalization of the energy shift that we had in the ground state. The difference there was that the NLM was, the second NLM was also 100. So in the ground state, it was the electrostatic energy of mutual charge of two identical charge distributions. There was electrostatic energy of those two mutual electrostatic energy of those two identical charge clouds, whereas here the charge clouds are different because they're different orbitals. Now it's easy to see that J and L is real because the integrand is real. In fact, not only that, it's easy to see that it's positive. In fact, the electrostatic interpretation shows you that it has to be positive because the charge clouds repel each other. It takes energy to bring them, takes work to bring them together. Likewise, the exchange integrals are also real. It takes a little more work to see that, but not much, because if you just swap x1 and x2, which are dummy variables of integration, then this goes into its own complex conjugate. So the result is that it's real. It turns out the exchange integrals, in addition, are positive. So just like the direct integrals, these are also greater than zero. Maybe I should say greater than or equal to zero. It's remotely possible they might exactly equal zero if there was no overlap on the different size. But in any case, they're certainly not negative. And
excuse me, I have a quick question.
Yes.
I'm a bit confused because earlier we were looking at like the effect of the perturbations on the energy levels in helium, and we saw that like the first order perturbation on the ground state like overshot the energy, like it predicted an energy that was too high. But I also thought that our operator H1 was only able to increase the was only able to provide like positive valued corrections. So I'm not clear on what happens at higher values or at higher orders of perturbation theory, whether it brings you closer to the true value or not.
Okay, so there's two issues there. One is are the corrections positive, and the second one is, do they overshoot? So the corrections are always positive because the perturbation is a positive operator. That's always going to be true. So although we get this J and L plus and minus K and L, the J has got to be greater than the K because the net result has to be positive. We'll see. I'll show you how diagrammatically that's true. The second issue, does it overshoot? And that only happens in the ground state because it's really variational, you see. That is to say that if you're studying the first order perturbation theory of the ground state, the energy shift in first order perturbation theory of the ground state can be realized by means of a trial wave function. And therefore, that energy is indeed an upper bound to the true ground state. Therefore, it had to overshoot. But that doesn't mean that the excited states are going to overshoot. They will raise the energies, but will they go too high or will they go too low? That's an open question.
Okay, but then
Okay.
if we're only considering the ground state, but we're considering going to higher orders of perturbation theories on the ground state energy, will the second and third, et cetera, orders of perturbation theory, like for some reason, no longer necessarily increase the energy shift?
Yeah, so there's a homework problem coming up on that. It has to do with the extent to which the results of perturbation theory can be interpreted via the variational principle. So I'll let you think about that for the homework problem. Then if you want to, we can talk about it at office hours.
Okay, thank you.
Okay, all right. Okay, so both these integrals are real and positive. The positivity of the exchange integral can be proven by means that I prefer not to go into, partly because there's a good physical reason for it, which I'll tell you about, maybe not tonight, but when I get, as soon as I can, soon I'll tell you about it, and it's important physics. So we'll see why that's true, why the exchange integrals are positive. All right, okay, so what does this do for the excited states then? So let's take, for example, the n equals 2 states. So these would be the 2s and the 2p would be the orbitals in hydrogen-like language. Of course, that's just the electron that's been excited. The other electron remained in the ground state, so it's in a 1s orbital. So we can describe the condition of these two electrons as either 1s, 2s, or 1s, 2p. This, by the way, is called an electron configuration that we're talking about. We'll say more about that when we talk about multi-electron atoms. In any case, the electron configuration is a specification of the quantum numbers of the single electron orbitals to the extent that the exact wave function can be approximated by single electron orbitals. In any case, this is what we have for the n equals 2 states of helium. So in a sense, there are really two levels here. There's the 1s, 2s, and then there's the 1s, 2p, which, as I say, are the quantum numbers of the unperturbed system. Now then, if we look at the 1s, 2s, the energy shifts are the j plus and minus the k. So there's a j20 here, goes up like this, like so. And then by doing the plus and minus the k20, we get one here, which is a j20 plus k20. And the lower one, which is a j20 minus k20. And remember that sign is the sign of the spatial exchange symmetry. Likewise, for the 1s2p, it turns out the j21 is larger. Numerically, it turns out that way. And then the k gives us, again, a plus and a minus. It looks like this. So you have j21 plus k21 and a j21 minus k21. All right, now then, so these then gives us 4 levels here, which are what are predicted by first order, now degenerate perturbation theory for the excited state, for the n equals 2 states anyway. So what quantum numbers do these correspond to in the real helium? Well, these are all of them are capital N equals 2, because they're coming from the n equals 2. They're perturbing the n equals 2 levels of the singly excited state. So capital N is equal to 2. If the lowercase l quantum number is 0, that is to say the 1s 2s state, then the capital quantum number l quantum number is 0 also. So these are the s states here. These states here are capital L equals 0, whereas these states over here are L equals 1. That's because these came from the P. And then the plus and the minus govern the spatial symmetry, which by the rules is connected with the spin symmetry. so that the plus state is spatially symmetric, therefore spin antisymmetric, therefore it is the spin singlet. So this state then is the n equals 2 spin singlet S. Whereas this state, being with it spatially antisymmetric, corresponds to spin triplet. This is the 2 triplet S. This state over here is now L equals 1, so those are P states. This is the 2 singlet P, and this is the 2 triplet P. And the way that I've drawn this diagram, in fact, reproduces the ordering of the energy levels that we see in the actual helium, which I've now probably lost here because I put so many things away here. I've lost it. But if you sketch these in our exact energy level diagram, you'll see that they at least reproduce the order in which the n equals 2 energy levels occur in actual helium. The lowest one of all is, by the way, notice the triplet states are, okay, yeah, so you'll see they come in the right order. Now, what about these features of the spectrum of real helium? In particular, what about the fact that the triplet states are lower in energy than the singlet states for the same quantum numbers? Why does that happen? Well, what we see here is it happens because the K integral is positive, so that with the minus sign, you get lower energy. The 2 triplet S is below the 2 singlet S, and likewise the 2 triplet P is below the 2 singlet P. So the positivity of the K integral is the mathematical reason why that's true. But there's a physical reason why it's true too, and it's really more important than the mathematical reason, something that's more worthwhile remembering. So let me tell you what that is. Maybe that's all I have time for tonight. It's interesting physically. The reason is this, is that if you increase the spin, leaving everything else the same, if you increase the spin, you're making the spin part of the wave function more symmetric. So if we go from the spin singlet to a spin triplet, we go from an antisymmetric spin state to a symmetric spin state. If you have more than 2 electrons, then you have more possible spin values you can run through. But basically, the higher the spin value, the more symmetric the spin state becomes. Therefore, by the symmetrization postulate, the spatial wave function must become more antisymmetric. Well, that means in the case of helium that of course the spin triplet states are ortho states, they're spatially antisymmetric. Well, a spatially antisymmetric state is one that is odd when we swap x1 and x2, whereas a spatially symmetric state is even. If x1 and x2 were one-dimensional variables instead of three-dimensional variables, you'd have a situation that looks like this. If you have something that's odd under exchange, it's a wave function that does this. Or if it's something that's even under exchange, it's a wave function that does something like this. In other words, an odd wave function. So if this vertical line is the line where x1 equals x2, then a wave function that's odd under the exchange of x1 and x2 has to vanish on the line. Whereas a wave function that's even under exchange has a maximum on that line. So what that means is that the odd wave functions, odd under spatial exchange, keep the electrons further apart. The probability of 2 electrons being on top of each other is 0 and low, that they're close together. Whereas the wave function that's spatially symmetric piles wave functions smack dab on top of each other where their Coulomb repulsion is maximized and raises the energy. So that's the reason why the singlet states are higher in energy than the triplet states. It has to do with the distribution of charge in three-dimensional space that's forced on the spatial part of the wave function because it has to have an opposite symmetry to the spin part of the wave function. This, in fact, is the same argument I gave you earlier about why energies depend on spin in non-relativistic systems, even when the spin contributions to the Hamiltonian are completely negligible. Notice the energies in question here are actually Coulomb energies. I can't remember what I told you about ferromagnetism. I think I mentioned it. But ferromagnetism involves the same phenomenon except larger numbers of particles. The reason the electrons like to be aligned, have their spins aligned in a ferromagnet, is because aligning the spins makes the spin states highly symmetric, which therefore makes the spatial state antisymmetric, which therefore lowers the Coulomb energy. So it's energetically favorable for the spins to align. Now, you have to analyze this in the context of the details of the condensed matter and also thermodynamics, because you have to worry about finite temperature and so on. But this is the basic idea behind this. And this is ultimately the explanation for ferromagnetism. This was first worked out by Heisenberg in 1926 or so. It was very shortly after he analyzed helium along the same lines which I've been presenting this last couple of lectures. This is really Heisenberg's analysis. Anyway, he also made the jump and realized that this was the explanation for ferromagnetism. Okay, that's all for tonight. Are there any questions? We're not quite done with helium, but there's a lot of material here, and I'll finish it up next time and then we'll move on to other topics. No questions? All right, if there's no questions, I shall stop screen share. If I can get my cursor on it here. And then I shall stop the recording.